Okay, good morning, everybody. Welcome to Big Data for Small Dollars. A little bit of a slightly fun presentation about big data and how you might make money out of it. The time now is 5 to 12. I'm to stop at 12:45 because it's lunch, but I'm aiming to stop at 12:35, so we have 5 or 10 minutes for questions at the end. If you've got a question in the middle, just put your hand up. So I'm Neil Stevenson. I work for Hazelcast. Hopefully we're all familiar with Hazelcast. In-memory data grid, streaming analytics, founded in 2008, open source, blah, blah, blah. But you might not know so much about me. My job is solution architect, so I help people with Hazelcast, help them use it. I've been in computing for quite a while now. I started work in 1989, so that's coming up for 29 years. I've started with in-memory data grids in 2010, and I've been doing streaming analytics since 2016. So there's a few things about me that you might say, coffee, I remember coffee. Java, I like Java. I started on Java 1.3 was my first version of Java. And I remember the first version of C++. I was a C programmer. I had to change. So let's start with a little bit of audience engagement. Who remembers Y2K? Who's old enough to have been working then? Yay, well done. This was what data records looked like back then. That's a postcode, the postcode of here, 1155 the time, 180625, the 25th of June, today, in other words. So this was how we would hold data on the systems that I started working with, because disks were very expensive. So this was big data. This was a problem for us. We couldn't afford 8 bytes to hold a date because we had lots of dates, thousands, even millions. So that would have been 2 or 3 megabytes just for holding 1 and 9. It was very expensive. So that's kind of where the big data comes from for me. I thought we'd start by defining big data. Storage costs money. Storage always costs money. Storage is always going to cost money. Storage has got cheaper, but data's got bigger. So really, in my mind, storage is losing the battle. So storage costs money, as in dollars, or pounds, or euros, or bitcoins, or whatever you choose to buy it in. But much more important is that storage costs time. Even if you've got rotating disks or flash memory, it's time to store your data. So the idea that you would store something and then process it is just not going to cut it. Even if you store it in memory, there's a time delay to storing things in memory, because generally with data you store, you need some sort of RAID, mirroring, some sort of store it in 2 places, so 3 places, whatever number you choose. So we need in-memory computing, which is rather convenient for today, because we don't want to store our data and then process it. We just can't afford it. We can't keep up. Data's coming in too fast or too much. We can't afford to store. Well, actually we can, but for the purposes of today, we're not interested in storing the input. So, UNIX command. Here's a UNIX command, ls, vertical bar, grep nil, vertical bar, wc minus l. If you're not a UNIX person, this is what's called the UNIX pipeline. Windows has a similar kind of thing because it's such a good idea. We have the ls command, lists of files in the file system, it's like dir. We have grep, which is a filter, only let through the files that match the string nil. So ones that got my name, my files. And then wc minus l is word count minus l, so count the number of lines. it's a simple chain of processing. We don't store the answers anywhere. Just input, input already exists, pass it through this chain, and we get some output. If we think of this in slightly greater detail, that first stage, the ls stage, is like a one-off operation. It prints out some data and then it's done. So it's kind of a source. The intermediate stage, the grep, is kind of active. Every line that comes in, it might pass on out. It doesn't wait for all the input before it starts doing anything. So it's a kind of continuous stage. And the word count at the end is a terminal stage, but it's a discrete terminal. It doesn't do anything until it knows all the input is exhausted. So in terms of counting, you don't know the total until you've got them all. You'll internally maintain a subtotal. So it's a fairly simple example, but if we kind of generalize it, what we have is a processing chain. This goes to this, goes to this. I've broken down my requirement into little atomic steps. I want to do this, and I want to do this, and then I want to do this. So the output of the first stage on the left passes to the middle stage, passes through to the right-hand stage. Processing chain, a pipeline. But straightforward pipeline is okay. Being able to branch is useful. So, hang on. In UNIX, that's the T command. You've got output that you feed on. And then suddenly we're starting to see, well, what is this? This is like the London Underground. How do you get to Victoria from King's Cross? Maybe it's a more complicated pipeline. Maybe it's a bigger chain of processing. Maybe this chunk feeds to that chunk and it's also taking data from that chunk. What we have here is two starts, two feeders for my data chain. And it all ends up at the right. I've drawn it left to right because that fits nicely on the slide, but top to bottom, right to left, whatever works for you. More generally still, you could have loops. The output from here gets fed back in. So it's a general way of thinking of your data. I've got data that comes in, I pass it to stage to stage to stage. I'm bringing data in, bringing data out, expanding and contracting, enriching, filtering, all these kind of things that start to become familiar with Java streams. If you've looked at Java's for each and how you do filters and maps and code. So, there's a little bit of the background. I did mention Hazelcast, so unsurprisingly, Hazelcast technology features in my demonstration. The one that features most today is Hazelcast Jet, because Jet is, hang on, there we go. Jet's Java-based, Jet is open source, Jet is Apache 2 distributed analytics. And the bit that matters is it's easy to use because it's a Java-based streaming engine. So if you're familiar with the other streaming engines, a lot of those are written in Scala or other kind of languages, and it can be difficult to find the developers. Very strangely, I had a conversation this morning. That was somebody's biggest concern, was finding and retaining staff. So Java-based, good to work with. I think it's really good, but there's a demo. You can download it. You can form your own opinion. So it's based around the idea of acyclic graphs. So the diagram from previously, just cut and pasted here. The only thing we don't support is feedback loops because that makes it difficult to do checkpointing and that kind of guaranteed once delivery. And it's a distributed version of acyclic graphs. So if you have 2 CPUs, run 2 copies. If you've got 4 CPUs, run 4 copies. However many you feel is appropriate. And what matters also is that once you have copies of these graphs, so once you have a processing stream and another processing stream, a clone of it, they don't have to be separated. You can send data from one to the other. So the output is collated at some point. As I've drawn it on this graph, the most important thing is to try and push that data crisscross downstream, because the general idea is you have less and less data as you go on. No description of streaming is going to be complete without word count. If you've seen it before, here we go, here's another one. This is how it works in Hazelcast Jet. You create a processing pipeline. We're drawing data out from a map. We're flattening it out. We're mapping it, filtering it, counting, collating, and putting the result to a map, because that's what you do with word count. Just to see who's paying attention. Who can spot the mistake? Deliberate mistake? 10 seconds. No. I'll give you a clue. Filter. I've put the filter after the map. So I'm mapping output to lowercase, so I'm running a method and then I might discard it. It's more efficient to do it the other way around. And it's like, that seems a trivial thing, but if you've got millions of items of data, little things like that that's functionally correct can make a big difference. So you've got to have your kind of brains about you. I get this wrong quite a lot, because it's difficult. You've got to be aware of what you're doing. You've got to be focused. So, back to this diagram. We've got two instances of this job because we can parallelize the input. So if we had a piece of the map earlier was called Hamlet, so to be or not to be, then we could send some of that input to one graph, some of that input the other graph. Just focus on the word be because it occurs in both sentences. It can be counted. Hang on, this clicker's not working. There we go. So this graph has counted the word be once. This graph has counted the word be once as well. These might be running on different CPUs, soak up all the power of the machine. These different CPUs might be in different JVMs. You can have as many JVMs, as many machines as you can afford, and you can have as much processing power, as much parallelism as you need. And then the part that matters is the final operation, counting the B, is only correct if all the B's are mapped together. So that's where you're crossing data. Now, if you think, and update the result, these things take hours to do in PowerPoint. Now we go, B goes to 2. The important part is that moving data from here to here might be across machines. So you want to reduce it down as much as you can, so that, you know, if you've got 1 million records coming in, maybe only 5 go from machine to machine, because that will make it execute quickly. So we have a stream processor. Time for some big data. So let's define big. We've kind of covered it already, but sports seemed a good thing to pick because it's reasonably big, reasonably popular, reasonably well known. We don't want to do finance, too boring. Super Bowl in, was it January, February? 103.4 million viewers apparently. Fairly big. Super Bowl halftime show, 106 million people, so more people tuned in for the middle part than the whole game, because the game goes on a long time. But to be topical, the World Cup, because I've been quite interested in the football. I don't have the figures for the 2018 World Cup, but the 2014 World Cup had 1 billion people watching the final, and then obviously there was other games as well. You can click on these links if you can be bothered and find where I got the numbers from. But an interesting thing on the World Cup final, 280 million people were watching it on mobile or web. 78,838 in the stadium and 695 million on television at home. So the rest were in pubs and clubs. So 280 million people potentially tweeting because they're on their phones. So there's some big data, 618,000 tweets a minute. Now this is starting to get interesting for me and hopefully for you. So Twitter stores these tweets We don't have to. That's problem one sorted. We're not going to do the storage. What we want to do is look at the tweets and figure out who's going to win. What do the fans tweet about? What do people tweet about? Could be anything. But if we can analyze the tweets, we can work out who's going to win. Because one person might think that Scotland are going to win the World Cup, but most people don't. It's the most people. If the basis of sentiment analysis is around collective thinking. If everybody are thinking that England are doing really well because they beat Panama and the team will be buoyed up, well then that kind of helps. So, whoops, skipped on a little bit too fast, but the basic idea of my pipeline is I'm going to connect to Twitter and pull out tweets based on a hashtag. I'll do this live, and who knows what will happen because it depends on the hashtag. I'm going to filter out the ones that aren't in Western characters because my coding's for Western characters only. I'm going to take those filtered tweets and enrich them by determining what team they're about. Otherwise, they're not much use to me. If I can't find a team, discard it. If the team's not one I'm interested in, discard it, filter, filter, filter. And then the last stage really is around this sentiment analysis. What does the tweet say? What do I interpret that from? That's not stream processing, that's business logic. And then trivially at the end, produce some counts. Twitter has an application called Firehose where it's an API, you connect to it. So you could be pulling data out of Twitter in huge volumes, 618,000 tweets a minute, potentially. Always got to be aware of what's happening. This incrementing of the running totals, that might be contention point. You've got running totals in one place. But you can do routing on team names. Remember I said you could send data from JVM to JVM? But that's maybe not the place to do it. That's a better choice because it's further down. I've filtered some data out. So I can send all the tweets about England to one place. I can send all the tweets about Panama to another. Let's see some code. Now, I mentioned I don't know what's going to happen. We're going to connect to the internet, pull some tweets out of Twitter. The Uruguay-Russia game is on today at 3 o'clock. Go back. Here's something wrong with my coding. I'm filtering out ASCII characters, filtering in ASCII characters, filtering out everything else. So that's going to be wrong for Uruguay-Russia. There'll be a lot of people in Russia tweeting in Cyrillic. So that's going to give a skewed view. It's only a demonstration. You can download it and fix that yourself. If you like, join in. The hashtag for today's game, the official hashtag, if you look on FIFA, is UruRus. Uruguay, Russia. Uruguay are at home, although they're obviously in Russia, and Russia are away and they're in Russia. That's the way it works. So, does this actually work? Well, fundamentally, no. Well, more correctly, not like this. All I'm saying is my business logic here is not very good. It's like looking for individual words. As a concept, it is, well, it's just a little bit simplistic. But people do sentiment analysis. Somebody did sentiment analysis on stock market trading based off Twitter feeds. So again, they were doing that thing. And where they got it wrong, there's a company called Berkshire Hathaway, which are run by Warren Buffett. Their stock price went up because people were doing automated buys when Anne Hathaway had a good film. So you've got to be careful of sentiment analysis, but as an idea, it's a valid concept. If you were tweeting about Bitcoin price, Bitcoin's gone up, Bitcoin's gone down, that's what you've got to be careful of. People will try and manipulate the market by tweeting. If you have enough content, then you can exclude bias. But it has had some success. The Argentina-Croatia game, Argentina had a lot of negative comments, went on. You know, there's only 3. We've had 16 games so far, so correct predictions out of 3 is not like a winning strategy. I wouldn't bet any money on it. But as an actual algorithm, it's fine. We're taking data in and we're processing it. So, stream processing. When we're doing stream processing, we've got a stream of data. It's coming in from somewhere. Somebody else has already stored it. What I didn't show here is that you could be using an in-memory data grid as the source of your stream. You could be capturing data actions that you're writing to the grid. We do this when we can't afford to store the data, or we're just not interested in it, or we can't afford the time to store the data. We want to process it as it happens. So if you imagine it, it's the 600,000 tweets while the World Cup is going on, coming out every minute. We don't care to store those. We want to know, what are people thinking? Are Germany going to beat Argentina in 2014? It was only by 1 goal, so the whole sentiment there could have been worthwhile. And distribution is part of it. You don't think of it as a pipeline, think of it as pipelines running in parallel. So you can pull data in parallel, you can send it out in parallel, you can send data from one instance to another. The word count example. So if your machine has got 4 CPUs, you run 4 instances, you soak up all the power of the machine. If you've got 4 CPUs, you're running 8 instances across multiple JVMs. Multiple JVMs, multiple nodes. So just a final kind of thing, and then we'll go on to the last slide. All these things, you always think of questions afterwards. So if you need to, you can reach me as neil@hazelcast.com. If you want to try it, download the code from Neil Stevenson on GitHub. The demo is called World Cup with great imagination. You will need to create yourself a Twitter account as a developer. So go into, I think it's developer.twitter.com, and then when you create a dummy application, it creates, when you click the create application button, only then does it give you credentials. So create a dummy application, you never need to use it, and you get Twitter credentials, and then you can connect. I've not put my credentials on the demonstration because those are my credentials, and I don't want you then tweeting as me saying, I was at the Grid Gain Summit and Neil said that Russia was going to win, and in fact they didn't, and I put all my money on it. So, okay, good morning everybody.